Now we're we're just going to talk about the two realms of the LLM quantization. Actually, there's it's like, I wouldn't call it yin and yang. It's just like, you got Rolling Stones and you got the Beatles. That's how I see it. So enterprise solution is mostly vLLM or SLG or LM deploy and stuff. And then you have the consumer LLM, which is more the Llama CPP. So we'll be starting with the enterprise side of it, which is really, really sort of intertwined with the vLLM platform. So I'll let Eldar talk about it. Maybe he can even share his slide. Feel free to do so. We'll talk also about the weights vs activation and throughput latency. I'll have to ask you, like the difference between both activation, because I haven't seen activation on the GGF side. But feel free to share. If you have a presentation, I can put it on the stage. I think you put it here. Are we good?
Yeah.
Eldar?
Yes.
Okay. All
Yeah.
right. Perfect.
Let me just add. So based on there was this question regarding the quantization and the other architectures. Just to add on top of that, so if you guys are actually interested, you can go and Google for SparseZoo. That's actually like the repository that we used to maintain before Hugging Face became a thing, where we actually pushed a lot of the quantized like CNNs. I think I've seen CNNs here in the chat, like ResNets, YOLO models, and so on. That was actually what we used to work on when we were running models on CPUs.
And CNN is for like images and stuff. CNN is a convolutional neural network,
that's
right?
Yeah, that's right. Yeah,
I have good memory.
Yeah, and basically quantization works just fine there as well. It's just a matter of like optimizing for for slightly different layers, but it's more or less the same thing.
Just for the audience, CNN is, for example, used in like self-driven cars like Teslas and stuff, right? They can be used to like avoid obstacles and stuff like that on Waymo. Back in the days,
maybe. Anyone who started learning machine learning, I think that's probably the first set of lessons that they should
use
have.
Case? Okay.
I mean, no, like convolutional neural networks. I think that's the first intro, before LLMs became a thing. So
wow. Okay, that's the 250K, 56K modem version of quantization or neural networks. Cool. Go ahead.
Yeah. So you asked regarding the question was regarding the weights and activation and quantization. So,
yes.
Yeah. So basically, just kind of like the idea here would be just to show how the architecture looks like and what happens when we are doing forward pass, like when we are doing inference with an LLM. And based on that, we can figure out actually which parts we can quantize. So at the bottom here, like we always have the CPU memory. So this is a large memory. It's very large, but it's unfortunately slow. Then on top of that, we have the GPUs, so which have this high bandwidth memory. And this is what we see when we type NVIDIA SMI on our server. And this is much smaller memory, but it's much faster. And then on top of that, we have the GPU Astra and Tensor cores. And this is where actually the computation happens during the inference pass. And this is the smallest part of the memory, but it's also the fastest. And when we want to run inference with an LLM, what we are doing, we are loading the model from CPU to GPU. And this is something we do usually just once. So more or less, this is not that impactful in general, apart from some specific applications which actually care about the loading time. And then during the runtime, what we are doing, we are loading the models from HBM into Tensor cores. We do the computation there. We chunk the layers, do matrix multiplications and so on, write back the results and repeat. And this is something we do n times, because we do this for every single layer in a network, for every a linear operator. And basically, because we are running this n times, these are the two main operations that we want to accelerate during the inference, loading of the layers from HBM into the Tensor cores, right, and SRAM, and actual computation that happens in Tensor cores. So these are the two main operations. For the first one, for the loading part, so the way to accelerate this, so we cannot do anything on the server, right? So it comes with a predefined transfer speeds. So it's what we have. So the only way to get the speedups there is to actually reduce the number of bits that we need to load. And that brings us to this weight-only quantization regime, where we just get the speedups because now we have less bits to to read through from HBM. The second part is computation part, and this is what I mentioned before. The computation happens in tensor cores, so the only way to speed up the computation is to use faster tensor cores. And then if you look at the specs of H100, we see that the BF16 tensor cores have, like as I mentioned before, like around 2K teraflops. But then the GPUs also come with int8 and FP8 tensor cores, and these have like 2x more teraflops. And basically, the way to kind of get the speed up during the computation is to quantize both weights and activations. So we want to quantize both operands that go inside the matrix-matrix multiplication operation, and that's when we do weight and activation quantization. And this is how we are optimizing now the computational part of that. And yeah, this is just a note. FP8 tensor cores are available only on the newer architectures like a Hopper, H100, H200, and other Lovelace like L4TS, for example. Whereas int8 is available on Ampere and all the other GPUs. And yeah, this is the motivation to quantize both operands in case we are in this compute bound regime where we want to get more flops, in a unit of time.
So the weight part, I totally get it. But when you talk about the compute, right? So the compute happens at the tensor core level, right? What is represented by the compute, right? So like I'm loading the weights, and then eventually something called the key values, key cache, and where is that computation happening in the tensor core once the model is fully loaded, right? And you're doing inference. We're not talking about training. I'm sorry, I'm really focusing on inference today. But so when you're doing inference, your models are loaded. You split them into. You took FP8, and then you're talking about activation here, right? Which is the compute, right? What do you mean by computation in tensor?
Yeah, so if we look at the LLM, like how it looks like at the first layer, like the very first layer that we have are the input embeddings. So we have some text. We tokenize the text, so we convert the text into just some integers. Mm-hmm. We pass the tokens through the input embedding matrix, and this is going to convert every single token into like some n-dimensional vector, right? And then we get like some input batch of our tokens represented in some embedded into this n-dimensional space, right? And this is going to be some large matrix. And then the very first thing that we need to do is we're going to multiply that with the first layer of the network. And the first layer of the network, for example, is let's ignore normalization layer. It's going to be like Q projection, K projection, V projection, for example, or in the MLP part, like up gate or down projection. So basically, all of these layers are represented with one linear operator, which is literally a matrix, like number of input features times the number of output features, and we multiply that matrix with this input batch. And this input batch is called activations. And these are that's the first operand, like input activations. The second operand are the weights. We do the product, and then we pass this to a next layer, right? And then the next layer gets this output of the previous layer, which are now the input activations for this layer. We all again do the matrix multiplication. We pass it on. And this is basically the inputs before we do the matrix multiplication at every single layer. Those are the activations that we are quantizing. Because once we want to do like input activations times the weights, we have to have both operands in either FP8 or int8 in order to leverage these lower precision tensor cores. So we quantize the inputs, and then we already have quantized weights, which we quantized before, for example, and then we multiply them with kind of 2 times more teraflops. And then we pass it on to the next. So basically, it's just the inputs for each layer. We quantize them before we do the A times X operation.
Right. So the weights, that's the loading part, but the computation is your input. It's any prompt that is going to be tokenized and going through every layer until the decoding would happen, and then the end user would have the result, right? So like every layer, whether MLP or any other layers or norm layers, there's a computation happening based on like the embedding that would have been produced based on the input. And this is the calculation that you're talking about. This is the activation side of it. And well, while you can have like a lower bit weights, you could still have full precision activation. Is this what you mean as well?
Yes. So that would be the case for weight only quantization. So I think that's what the Colin will probably tell you more about. So that's the setup where we are not quantizing activations. So like they are flowing in the full precision, and we are just quantizing the weights. And the main caveat in that case is that if we are on GPUs, then we cannot leverage the FP8 or Int8 tensor cores, because the inputs are, let's say, BF16, weights are int4. So we cannot use FP8 or Int8 tensor cores to multiply them. And that's why we don't get any acceleration on the computational side. But we do get the acceleration for loading, because we are loading less bits.
Excellent. I'll keep this on ice for Colin when he'll start to talk about GGUF. All right, carry on, Eldar.
Yeah, that's basically it. Yeah, I think I can probably stop here. Like, but
great.
That would be the main motivation and the reason why we're doing the activation quantization as well.
Perfect. Interesting. Thanks so much. And obviously, there's the quantization can happen on GPU. It can also happen on CPU and also on ARM, TPU, and many other Gaudi from Intel as well, right? So this is not just on GPU. This is also on CPU and ARM. And I think in your previous presentation, you said that depending on the kind of hardware you have, there is maybe leverage you can use with quantization, activation quantization. Sometimes you can keep it at 16. Sometimes it's better to split it in two. But it's not always like there's no rule of thumb. It depends on the case, right? But you can leverage activation on other infrastructures, other chips as well, right?
Yeah, it's always, it's mostly hardware dependent. So you look at the hardware at which you're deploying your model, then you see the specs. For example, in H100 case, we have FP8. That's going to be the default choice. Let's go to FP8. But if you don't have FP8 tensor cores, literally the only option you have is then Int8. So it's not like you have a choice. But for example, there is also a question about FP4. If you have B200, if you have B200, then you can actually choose. I can do FP8, I can do FP4. It's more or less like what's the trade-off that I'm willing to accept for my specific deployment.
And here we're talking about FP4 quants weight related. Eventually, if the hardware doesn't support FP4 tensors, you could still quantize the weights.
You can quantize the weights, yes. You just need efficient kernels, which are going to be able to unpack properly the packed weights for the inference. But you will not be able to get the computational speed up from faster matrix multiplications, because you don't have FP4 tensor cores on that specific GPU. If it's not Blackwell, of course.
It's relative, right? When people say fast, what do you mean by fast? Faster load-in or faster computation? And sometimes, even latency and throughput are two different things, and people sometimes confuse them. I don't know if you can have if you can talk about. Maybe we can talk about it later, but basically, which one is memory bound, which one is compute bound, for example.
Yeah. So the main distinction there is it's that specific a threshold, whether something is memory bound or compute bound, really depends on many factors, like number of queries per second that are hitting your deployment, size of your model, size of your GPU, and so on. So that's really something that usually you should do proper benchmarking for your model. So this is my GPU, this is my model. And I can now simulate, these are the workloads that I expect to get, like the input size, this one requests, and then you simulate that, and then you benchmark, and then you see actually where this flip happens. It's very hard to tell it upfront, you will be in this or that regime. For some cases, it's easy, just when you say, it's a very small model on a very large GPU, or like I have just maybe like 2 requests per second or something like that, that's more or less indicates that you'll probably be in this memory bandwidth bound regime. Whereas if I am deploying, I don't know, like DeepSeek, and I'll have like, like 100 queries per second coming in or something like that, then most likely you will be in this other regime, which is bounded by compute.
Gotcha.